why element quality or mesh quality is important. So poor quality mesh, we know it results in poor convergence issues and inaccurate results. Let's try to understand this with a mathematical explanation. Before that, let me talk about nonlinear solution method. We will discuss this in detail in chapter 5. But for now, let's understand that nonlinear analysis is solved in incremental and iterative method. Okay. In short, the stiffness matrix is updated in each iteration. So let's consider this concept for now, which we will see in detail later. So with that, we know we have seen this in earlier chapter, on the last lecture of the chapter 3. That this element stiffness matrix is for quadrilateral element, 2D element, and this one is in XY global coordinate system, whereas we have discussed something about Jacobian matrix and natural coordinates. So basically, what we are doing, we are writing element stiffness matrix from global XY coordinates to natural local natural coordinates zeta eta, and this mapping is basically done with something called Jacobian matrix. So this right side form of element stiffness matrix, we have written it in form of natural coordinates zeta eta, and we have this determinant of Jacobian matrix. And we also understood what is the physical significance of this Jacobian matrix. Basically, Jacobian matrix is relates derivatives of partial derivatives of global and natural coordinates. So we know this is a mapping. Basically, Jacobian is the mapping between global and natural coordinates. So if I have element something like this in a global coordinate system, and with the help of Jacobian, I can map it into natural coordinates, something like this. Okay. So basically, the Jacobian is a size and or shape factor. So if element is bigger or smaller, it will turn it into uniform size. Okay, that is 2 by 2 element size in case of quadrilateral element. And it is also shape factor. That means if whatever element shape is quadrilateral, skewed, okay, it will also turn it into a square element. So with this understanding, and this was a basically recap of previous lecture. Let's try to understand why poor element quality results in a poor convergence issues. So as we can see here, the J, as we said, it is a scaling, right? It is shape or size factor. In other words, we can also say the J is element scaling or mapping. That means element will expand or shrink when it goes from global to natural coordinate system. And J is also used in numerical integration of this element stiffness matrix, right? So this J will go into this, for example, this quadrilateral first order quadrilateral element. We have seen this is 8 by 8 matrix. So this J will go inside the matrix, and it will also multiply with each term in the 8 by 8 matrix. So J is also used in a numerical integration of this element stiffness matrix. Now J can no we can also say it is a element quality parameter, okay? Because as we said, it indicates how much element is scaled or mapped, okay? Expanded or shrunk, or it is skewed, unskewed. So that is indication of element quality. So let's see if the determinant of j is less than 0, that means the element is inverted. That means the area of element, okay, area or volume of element, it is basically flipped, okay, in a global coordinate system, and that is the reason mapping becomes negative. And this is also uh, leads to incorrect mapping. So j less than 0 is not acceptable. When j is equal to 0, okay, this means the element in global coordinate system is highly distorted or it is completely collapsed element. In this case, when j is equal to 0, the determinant of Jacobian matrix is equal to 0, we cannot compute element stiffness matrix, okay, because the terms are 0. This is also like here, as we said, it is area or volume of element is less than 0, okay, negative volume. In this case, the area or volume is equal to 0. So in this case, the element stiffness matrix becomes singular, and we cannot compute or we cannot do numerical integration for element stiffness matrix. So solver, nonlinear solver may fail. Okay? So this is also not acceptable. Now the Jacobian matrix determinant of that Jacobian should always be greater than 0. Okay? This is not sufficient. Okay, even in case of greater than 0, if it is a too low or high, that means the scaling, right? The scaling is very poor. Okay? Uh, for example, if we have four elements, okay, and there is a one element which is highly distorted, okay, and for this element the Jacobian either is too high or too low. In this case, the Jacobian uh, the transition of Jacobian is very abrupt from one element to another. So this also leads to a numerical instability, because as we have seen, the Jacobian is directly used in computation of element stiffness matrix. So this is also called poor conditioning. Okay. When Jacobian is very high or very low. So there is a particular range of Jacobian which needs to be maintained. Now let's talk about this quadrilateral element. As we know, it has four integration points, and this is a Jacobian. So we know the Jacobian has terms of zeta and eta. That means we can calculate Jacobian at each integration point. After computing Jacobian at each integration point, for each element, okay, for example, this particular first order quadrilateral element will have four Jacobian values, okay, at four integration points. Now, in many softwares, the Jacobian range is 0 to 1. So how this is calculated is it is a simply a ratio of it is a lowest to highest value in that element. Okay? So Jacobian is lowest Jacobian to highest Jacobian among four integration points. If it is a first order hexahedral element, then it is eight integration points. So basically Jacobian is the ratio of lowest to highest Jacobian value within that element, okay? And that's why we get the range as 0 to 1. So when Jacobian is equal to 1, the ratio is equal to 1. That means we can say the lowest and highest Jacobian among the integration points are the same. That means the original shape of element in global coordinate system is a perfect square. And when it is 0, so the uh, element area or volume in xy coordinate is 0, okay? And that is not acceptable. So the acceptable value of a Jacobian is it should be more than zero point 0.5 or zero point 0.6 depending on industry standards. And so now we can easily understand like why element quality is important. Okay? We have tried to understand it with mathematical explanation because it is used in a computation of element stiffness matrix. Okay? And this element stiffness matrix gets updated in each iteration in nonlinear solver. And if element gets distorted, okay, the Jacobian leads to a very low value, and in that case the local stiffness matrix will become very low, which will result in numerical instability and convergence issues. Hope this is clear. Now let's see some of the element quality check guidelines. Okay, before moving to discussing element quality parameters, okay, what should be our approach to solve a particular FEA model? So from my experience, the first thing is that when we get the model CAD model, we should not mesh the complete model with highest mesh quality, because we don't want to spend a lot of time in pre-processing level doing maintaining the highest mesh quality in each region. Okay, that might not be necessary. So first thing is, the when you want to do a first cut analysis, try to maintain a moderate quality mesh and perform analysis. Then based on results, anyways we are going to improve the mesh quality in a critical region. So that is sufficient. Critical regions means where the stress gradients are high, okay, which is your interest region. So improve the element quality only in those critical regions. And when you have not so critical regions, okay, we don't want to spend pre-processing time, okay, improving quality in that region, because we are not interested in probing or tracking stresses and strains in those regions. Yes, it should not be that it is too poor quality in not so critical regions, but we don't want to go extreme high quality elements in that region. Okay, so this is basically a trade-off. We need to strike balance between pre-processing time, that is the time spent in uh, generating high quality mesh, and the convergence behavior. So too poor quality means convergence issues, and very high quality mesh means high pre-processing time. So we need to strike a balance between these two things. And the guideline is simple. Okay, maintain high quality mesh in critical regions, and maintain moderate quality mesh in not so critical regions. With this, in next lecture, we will see different element quality parameters, and we will try to understand physical significance of them.